So basically, this is the project that started late last year, and it's currently supported by the grant from Ethereum Foundation. And I'm not going to details why I'm doing this, apart from the fact that I'm actually enjoying doing this, but you probably understand why we need to optimize Ethereum clients, right? So this is the outline. Hopefully that will help you decide whether you want to stay till the end, or is anything interesting there that you want to hear about. Let's go in. So I'm not going to go into the Merkle trees, sorted and unsorted, so let's go straight into the why this slide is here. So essentially, my first assumption about why the Ethereum network was inefficient around, for example, around the time of CryptoKitties and further down, my assumption was that it's something to do with the state, something to do with the slow access to the state, and that assumption was based on my profiling results from Geth. This is how the whole thing started, and I'm now started questioning this assumption, but this presentation has not reflected it yet. And in order to understand the access to the state, we need to understand how the state is stored in Ethereum client at the moment. So let's start with the Merkle radix tree. So if you, let's say that in this example, you want to store a dictionary of 4 values in this kind of structure, and you can clearly see where every word goes. So the path in a tree represents a key, and somewhere on the leaves there are values. And the reason why it's called Merkle, because there's a hashing going on. Every triangle is essentially concatenation and hashing. And then the result of the hash is inserted upwards. So essentially, in the end, you get the root hash of that radix tree. So in Ethereum, this is like how the state is essentially a dictionary of key to value. But instead of the radix 26, as you have here in Ethereum, the radix is 16. So that's why the tree is hexary. The problem with the radix trees like this is that you very often, if your keys are randomized, then on average you will get a lot of the segments which have really long segments with the branches of one element. And this is very inefficient because you usually allocate the whole 16 elements and you only use one. So you have like blow up. So when you store this data in memory, it uses much more memory than you really want to. And the solution to this is called Patricia tree, which is really an acronym. And the idea is that when you see these long branches of the unoccupied nodes, you replace them with either leaves, if this happens at the end of before the leaf, or you replace them with extension. And so this is how it gets transformed. So that it's much more efficient in terms of storing it in memory, and this is exactly what Ethereum state is doing. So instead of storing it in a simply Merkle radix tree, it stores it in this Patricia tree. It does have some disadvantages because the code to handle this tree is much more complicated than the code to handle usual radix tree, because you have lots of corner cases, like what happens when you got that extension, what happens when you get this and that, especially when you start deleting things. Sometimes, let's say that in our example, if you delete v4, right, and then that branch turns out into the branch with only one element, then you have to merge the extension to the leaf, and then this is kind of the corner case which has to be handled. Anyway, okay, so now this is very quickly, like some people ask me, like, what is ROP? ROP is used throughout of the Ethereum protocol, and usually as a dApp developer, you don't need to care about ROP, but if you start looking into the Ethereum client code, you need to have an idea what it is. And essentially, it's a way of encoding arbitrary data structures, and it has 5 different cases, like a case of just 1 byte, a case of array of bytes, short array, long array of bytes, and essentially recursive array of structures. And it uses some clever encoding. Essentially what it allows you to do, take any data structure in memory, encode it into a string of bytes, and then decode it back. And that will help us understand how the state is actually stored in most of the Ethereum clients today. So as I said before, the state is stored in the memory. When it's in memory, it's stored in this Patricia tree, which is on the left. And then on the right, this is how it's stored in a database. So the keys are essentially hashes of the ROP serialization of specific nodes, and like you have as many keys as you have nodes in Patricia tree, and the values are essentially these strings of bytes which represent the ROP encoding. And so now let's say that we are running out of memory for storing this current state, and we decided to offload, let's say, elements, this first top elements with the pink and yellow ones, right? And we essentially remove them from memory, and they are serialized on disk, but we don't have that branch. So now let's say that another transaction comes, and this transaction wants to reference, let's say, V1. So what we need to do, we need to fetch this from disk. And what actually happens, is it laser, right? Okay, so here, look, we only have the hash of that little subtree here, but we also know that this hash is actually SHA-3 of ROP of this node. So we look up, we get here, we get back the ROP of this little branch node, we deserialize it, and now we have this bit, but not this bit yet. Okay, so now we know the hashes of these little leaves. So because we need V1, we take that hash and we do another lookup, and then we get the serialization of that, and then we basically materialize it now. So now we've got this branch in memory, and now we can apply our transaction. But imagine, notice what happened. We actually did two lookups to database. One to get this little branch, and one to get this little leaf. And you cannot avoid having them sequentially, because in order to do this lookup, you need to know this hash. But in order to know this hash, you need to first do this lookup. So there's a data dependency here. And that data dependency means that the depth of this tree actually matters. The deeper is this Patricia tree, there are more lookups you need to do to essentially unroll that tree. And that's one of the reasons why, in Ethereum, before you insert anything into that tree, you have to first hash it with this SHA-3 hash function, which serves as a randomization function, so that the tree becomes balanced and then it's not too deep, because the maximum depth is currently 64, but on average, I think the usual depth is about 8 at the moment with the current size of the state. So it doesn't have to go all the 64 deep. Anyway, so this is how it's actually quite old, because we are currently coming to the block 6 million. I think it's probably going to happen tomorrow. But this was a long time ago, but still it demonstrates that so what this picture represents, here we have the levels of the Patricia tree down to the 12. There was nothing after the level 12 because of this balancing. And here you have the occupancy. So this is the occupancy 1, which doesn't happen in Patricia tree because it's been replaced by the extension nodes and by the leaf nodes. And so what you see here is essentially these extension and leaf nodes. And so here you get the 16, which is a fully saturated. So essentially level up to 4, from 0 to 4 are fully saturated, which is okay. And then you start having those little holes, and as I said, most of the elements would live on a level 7. I think by now it's probably moved to the level 8 because there's quite a bit more state after that. So, but this picture basically shows us again that the depth is actually important. So you can say that on average you have to do 7 lookups if you start from the top. Okay. So now what the Turbo-Geth is doing, the Turbo-Geth is a radical departure from that storage model, and it tries to say, okay, like, I understand why people wanted to store the state the way it was, because it was very convenient to get the root hash of the state to put it in a block. But what if we didn't do that? What if we just store the things as the key value pairs, as usual, like you usually would do in a database? But then the problem is that how do you compute the root hash? And so the way you do it is that, let's say, again, we wanted, this thing wasn't in memory, and we wanted to materialize it. What is that? So essentially what we do first is we realize that this is 1, and we do range queries on the database, which you could see that probably pretty simple. And in the return, you get this pair of key value pairs, and then you apply this Patricia tree hashing algorithm to derive this whole bit. And then you can work with that data. So that is basically a trade-off. So you do more computation to recompute these parts of the Patricia tree, but in return you get very nice and flat structure of the database. And that structure allows you to, let's say, do RPC queries much more efficiently because you simply query what you want. There is a little bit of complexity to that when we're going to look at it later, when you actually have to look at historical data. So this applies to the current state. But the most crucial bit here is the depth does not matter. In this model, it doesn't matter how deep the Patricia tree is. It does not affect the performance of the queries. Because it doesn't matter whether these elements produce the 64-bit deep subtrees, or is it one level deep. Right, so now we're going to talk about the processing architectures. So if you open up the Geth, probably other clients as well, so what we will see there is that you get this state in a database. So I think whenever I click, there's this flickering, or maybe it's over there. So then there's a state forest. The reason I'm saying forest and not a tree is because actually the Geth at least stores, let's say, 128 past Patricia trees, just in case that there's the reorg, so it can quickly go back to the previous tree and start building the fork from there, because it would be expensive to try to fetch it off from disk with all these lookups. So that's why I say forest. And then whenever you have a new block processed, there's a transient state, which is basically in memory. There's like a little hash map, which maps accounts to the account information and storage indices to storage information. And when the block, so the virtual machine does that, it interacts with this transient state. And when the block is finished, the state is committed into the tree, and then the tree computes the root hash, and everything gets committed to the database. But everything goes through that tree. And when people do an RPC request, they normally also go through the tree. So essentially, they don't go straight to the database, they always go through the tree. And let's say that if you have a query, which is very often used by exchanges, let's say you have a range of blocks, let's say block 10 and block 15, and you need to figure out which accounts have changed within this, changed anything about them, let's say nonce or balance within these blocks. This query will have to unroll these big trees at the block 5 or at the block 10 and at block 15. So that's actually quite slow. Now in Turbo-Geth it's a little bit different. So the main difference here is that the RPC queries would not go through the tree but go straight into the database. I have not implemented this yet, but that's one of the last things to do. And then the reason why I can do it as well is that I provide a common interface to the database and the tree. So I wanted to decouple it as much as possible, so that virtual machine in transient state doesn't have any idea like where is the data is actually stored. Is it going to be Patricia tree, or is it going to be like some other tree, or it's going to be the database. Now let's go to some data. So this was actually this is already quite old. But anyway, so the experiment here was that to run so it was a Google Cloud. The machine had 26 gigabytes of memory. One of them has SSD, one of them has HDD, and I set the limit on 5 million nodes in the Patricia tree, and you could see that it synced in about 12 days. Right, to that block 2.28. And you see that the HDD was actually falling behind. Anyway, so now this is how the memory did at that time. So you can see this is where the limit of 5 million started to kick in. But you can see like there's still something going on. I need to look at it further. But yeah, the memory didn't go up more than 6 gigabytes. Now this is another very interesting thing. So imagine that we have a huge amount of memory. So at the moment, I think you need about 70 gigabytes of memory. And so you never actually have to do this disk fetching operation for the state. You only save the state, but you never actually read it. And then it syncs in about 5 days. This is comparison to when we limited to 5 million nodes, which is quite interesting, which will be relevant a little bit later. I will tell you why. So, and in terms of memory consumption, it went up to 68 gigabytes. But you know, it synced in 5 days versus 12 days. Okay, so we will come to that a bit later. So now let's have a look at the disk consult. So this is archive node, which means that it actually preserves the total history of state, like unpacked, so that you can always query the state at any historical point. And as we can see here is that it's actually not too bad. So for archive mode to have this, because in comparison, I think the Geth has more than terabyte to achieve the same thing. And what we could see here is that, yeah, on the next slide, the clicker stopped working. Okay. Okay, so did I miss anything? Yeah, so basically that's it. I think this is really good. I will try to get it even further down. Now let's think about light clients. In the beginning, I completely ignored the issue of the light clients because I think it would put too much pressure on me. And also I decided not to support fast sync because actually fast sync relies on this Patricia tree is always present in the memory. So if we look at this protocols, one of them is called ETH and one of them is called LESS. So these are basically the two DEF P2P protocols that are running in the Ethereum network. And one of them is supported by let's say, the usual nodes, another one by light nodes. And I looked at each of them and I tried to figure out which one I can support quite easily and which one I cannot at the moment. And the ones I cannot support at the moment is this one and this one. So what the get node data does, get node data essentially is giving your hash inside the Patricia tree anywhere, at any point in history or any point in current state, and you're supposed to give it back the RLP of that. I cannot do that because it doesn't give me any information where in the history it is. And I cannot, even if I wanted to, I don't know, like, it doesn't tell me, oh, that was actually for a block 1000. It's just a hash. I don't know, like, I don't have all these hashes. So, and the get proofs is a bit easier because when the light client asks for the proof, it actually tells you the block number and it tells you which account it's involved. So actually it's easy for me to find it. So I will be able to support light clients much easier than a fast sync because what I could do is that I just simply for the purpose of supporting that, I can keep a little bit of a history of the Patricia tree, maybe like 10 blocks in the past, and hopefully the light clients will not ask for too old data. And if they do, then they say, oh, sorry, I don't have that anymore. We're past that point. But I will keep thinking about this. So this is kind of the very recent thought about light clients, because I realized I will have to do that at some point. Now, okay. So now let's get another look at the storage requirements. So at some point in the development, I decided to split up the current state from historical state. It used to be that I treated the current state the same as historical, but just with the latest block number as the history. And then I realized that if you separate them, the queries to the current state become more efficient. And then what I also realized when I did this graph is that the current state isn't actually that big. Do you remember I needed 68 gigs to store it as a Patricia tree? But when I store it as a B tree, which is how I represent in the database, it takes less than 10 gigabytes. So there's basically almost 7 times factor blow up when you're stored as a Patricia tree in the form that it is now. So it's actually possible if you store it in memory in a different format, let's say as a B tree, it's possible to like do 7 times compression, and probably it will be slightly faster as well. It's one of the things I will definitely try. So and that the reason why it's interesting, because do you remember how the sync time goes down from 12 to 5 days? So my theory is that if I implement this as the B tree instead of Patricia tree, I will be able to get the sync time down at the cost of extra 10 gigabytes of memory, right? That would be quite an interesting experiment. So now, another thing I don't like at the moment is this. So this is the artifact simply of Turbo-Geth. It does not exist in Geth. And what it is, essentially, for each block number, it stores which keys have changed in this block number. And the reason why I need this information is, first of all, it allows pruning very easily. I haven't implemented pruning, but this information will make pruning trivial. Because essentially, if you want to prune everything up to this block, you just consult this part of the database and just prune it, and just delete everything. And the second reason why this information is useful is when I do reorg, I look back, let's say that I do 10 blocks back reorg, I look back here, which keys have changed during these 10 blocks, and then I know what to undo. So basically, I roll back the Patricia tree 10 blocks back using this information, and it works actually pretty well. But in the future, I want to get rid of that chunk, and I will tell you how. So what is my current thinking of this? Although I think the RPC queries will be faster than in current Geth, but not fast enough. And the reason for that is, so imagine that we have the database, and in the database you've got the B tree, which is the most popular structure. It gives you ordering on some kind of keys, and in our case, it's an account. So let's say that it allows you very quickly to find any specific account, right? This B tree in a logarithmic time. But you also have another dimension, which is a block number. And because this particular B tree doesn't give me 2 dimensions, I have to basically hack around it. And what I do is that I encode this block number and I append it to the key, right? It's a bit hacky thing to do. It still allows me to find the account very quickly, but it doesn't allow me to do slicing on the particular block very easily. Because let's say that I want to retrieve history for block 339. And as you can see that the current state only includes this little blobs. But there are lots of blobs in the middle which are really old state, or the state they already have been deleted. Do you remember there was this attack on 2016 where there's lots of empty accounts being created and then subsequently cleared up after the spurious dragon hard fork, and that situation created a lot of empty accounts, and that would slow down my queries because there would be lots of things in between, and I had to basically walk through all of them to just collect the current state. So what I really need, I need a database which allows me to do the key ordering, but also a temporal element into it. So I started to look at the papers, and I found out that there are papers on it, which is like the first one, which I quite liked, is from 1996. And I think it's probably implemented in some products like Oracle or Teradata or Microsoft SQL Server, but I haven't found open source implementations yet, and probably I won't. And then there's other improvements on this. It's like how do you do bulk updates in these multi-version trees. So, and to give you a quick idea about what is the difference between a usual bit tree. So this is a usual bit tree. So the idea is that you've got these pages, which are normally like 4 kilobytes long, and they usually match the amount of data the minimum amount of data you read or write to the disk, like 4 kilobytes. Even if you want 1 byte, you still operate in chunks of 4 kilobytes. And so all the values are stored in the leaves of this tree, and these keys they work as guides. So you can know which page to descend to when you're looking for a specific key, right? And because they're all together, it gives you very nice locality and plays very nicely with the block devices like disks, plays very nicely with the caches on the CPU. And in fact, the interesting bit about it, there used to be another tree structure called T-tree, which is basically like a B tree, but optimized for memory. But then with the modern computer architecture, B tree actually outperforms that T tree because of the locality. So now the multi-version B trees are slightly different because for each key or each key value, you also have timestamp when it comes in and timestamp when it goes out, or the star if means that it's current. So my idea is essentially try to implement this based on that paper, on the first paper I had before. So I started doing this already, but let's see how it goes. So my hope is it's going to improve the whole query even further. And now let's look at the status. I'm really happy about this first line. So finally, after let's say 2 months of work, I managed to get the Turbo-Geth not just sync to the main net, but also stay synced. It basically follows the tip of the chain for the last 60 hours now, without break. And now, another interesting thing it does is actually it has some slight side effect. Because Turbo-Geth does not support like it cannot, like Geth, for example, if it gets conflicting blocks, it tries to execute them all, just in case somebody starts building on top of those blocks. So in Turbo-Geth, I cannot do that. I have to decide all the time which is the current block in the canonical chain. So I have to keep reworking, but that means that I have to keep all the ankles in the database. So it doesn't actually take a lot of space because all the ankles still have a proof of work, so it's actually hard to produce them. But it gives me a nice history on all the ankles that were ever propagated around the network. And one thing I started to see in the last couple of days is that there are sometimes really deep reorgs, like 10 blocks deep or 15 blocks deep, which was kind of surprising to me. And next thing I will do is I will look into this ankle history and see which miner is producing those ankle blocks. Maybe they've fallen behind. And this is where, remember in the beginning I said my assumption was that the performance problem is due to the state access, but now I start questioning the assumption. Maybe the problem is not only that. Maybe the bigger problem is the peer-to-peer network itself is actually quite unstable. Maybe the peers are kicking each other all the time and disconnecting and reconnecting. And maybe the download protocols are slightly incompatible with each other. And that generates these big reorgs and network kind of being really, behaving really unhealthily and uncle rates spiking. Maybe that's the reason. So I'm going to be looking at that much more closely in the next few weeks. And, but apart from that, I will fix all the RPCs. Hopefully they will be much faster than Geth. And then I will release it to some early adopters. I will not do it to general public because simply I will not be able to provide adequate support to the general public. But I will be able to provide support to some early adopters who will. There are already some organizations and people who want to do that. They just want to run this node and see how it goes. And then I want to support retested, which is something which is coming out of the Ethereum Foundation. Dmitry is working on this. Essentially, retested is you need to add like a 5 new RPC requests to the Ethereum node, and that allows you to run all the state tests which already exist directly on your node. Because at the moment, the state tests are running through CPP, C++ Ethereum as a proxy client, and they did not directly run on the other implementation. So supporting retested would allow me to run the state test on Turbo-Geth, and hopefully that will be easily portable back to Geth as well. And I'm going to look into Hive. I'm not very I looked at the code yet, but I'm not really familiar with this. Yes, and then maybe in the version 2, version 3, if I ever get somewhere with MVBT, which is multi-version B-tree, I might swap the database. So there will be no backwards compatibility. And that's it.